electricity voltage or electrical potential. This is just the electrical potential difference between 2 points, or it could be the voltage of this point if we want to specify the voltage between these two and we just want the voltage of this. That means in reference saying that the voltage of 0 is at infinity. So let's say when the distance or r is equal to infinity. The voltage or electrical potential does not need to be confused with the electrical potential energy, and even though the formula will also be similar, the voltage is the electrical potential or the electrical difference in relation to the distance. So we can write it as the line integral of the electric field dot dl. The electric field by Coulomb's law is just the constant times charge divided by r squared. So here the voltage is this dl becomes the r, because r is the same as distance, and I can take k and q out of this integral, and so I just have that k q times the integral of 1 over r squared dr, and this part, this integral is just negative 1 over r, so the voltage is the negative of Coulomb constant times the charge divided by r, and this would be evaluated, could be from A to B or from B to A, or if I just want to know the voltage of this point and not in reference to this or to this, I want to say the voltage of this or at this point is B sub B, then I take as a reference point r equals to infinity. So I said that the voltage is equal to 0 when the distance is equal to infinity. So I have that this will be evaluated from infinity to r. So the voltage is equal to negative k times q divided by times 1 over r minus 1 over infinity, that is just 0. So I just have that the voltage is minus k q over r, because k is 1 over 4 pi epsilon sub naught. I can write it as q divided by 4 pi epsilon naught r, the negative of this. This is the voltage, and is quite similar to the electrical potential energy, just that electrical potential energy has a q, the other q here, because it's the attraction between two charges. And so the voltage now is, if I have that the electrical potential energy U is minus k q1 q2 divided by r, I can say that the voltage is just the potential energy is U times charge, or I have that the electrical potential energy is that the voltage is electrical potential energy divided by the charge, or that the electrical potential energy is the voltage times the charge. And this is intuitive because the voltage has units of joules per coulomb, and the electrical potential energy has units of joules and the charge of coulomb. Or you have that voltage joules per coulomb, you multiply it by coulomb or charge, and you have electrical potential energy. So now if I want to know the voltage between A and B, you say that the voltage, when you take as a reference of point, for example, B or A, you can say BB minus BA, and you know that this certainly would be the same as the negative of BA minus BB. But the other way to do this is that the voltage then would be equal to the, I have BB minus BA is equal to the line integral of, here line integral is just this. If I put this circle, means that it is a closed line integral, and if it is a closed integral, means that I'm doing a path, a circular path, or circular or not circular, but the issue is that I return exactly to the same point, and so that will be 0. So that's the, I wanted to say this at the end, but I will say it now. So the voltage, when we're talking about this circular path, is 0. So the closed line integral of the electric field dot dl is equal to 0. If I just take the line integral of E dot dl, then I have the voltage. And here I will take it, if I want BB minus BA, I will take it from A to B. But this is the same as, remember that whenever you are taking the integral from A to B, you can take, or you would get that same value if you reverse the order of integration and you put a negative sign. And you can verify it quite well. So it would be minus from, sorry, the, oh yes, so now from B to A of the electric field dot dl, and this is exactly the same as evaluating the, I have the negative here, and here this is the, is B A minus BB, and so have the same. So our new formulas are that the voltage is equal to the line integral of E dot dl. So voltage is equal to the line integral of E dot dl, and the closed line integral of E dot dl is always equal to 0. And when we have these 2 points, we are taking the difference between voltage of B and voltage of A. Voltage of B was calculated as the difference between here and a point at infinity, and the same for voltage of A, that is the same as just taking the difference from here to here. That is, if you would have put here, the voltage is equal to the negative K times Q times 1 over R sub A minus R sub B, but this is the voltage of one and this is the voltage of the other. So the voltage is the integral, the line integral of E dot dl. Now in the next video we will talk about the vectorial field analysis in the voltage as a, sometimes as a scalar field. Now just if we are talking about a conservative field, that means that the voltage, or in this case the voltage is our scalar field. If we take the difference between these 2 points, it doesn't matter if we take this path, whatever it be, this, or if we take this, or if we just take this. The voltage between these two will always be the same if I take this or if I take this. That means that we are dealing with a conservative field.